In this lesson, we will be learning some ways to solve problems using K-equilibrium. It is useful to know the equilibrium constant to see how far a reaction goes to the right to make the products. Okay, first, let's go ahead and find the equilibrium constant. You have a mixture of hydrogen and nitrogen. Here's hydrogen here, nitrogen in a vessel. And you're allowed to attain equilibrium. So that means the reaction has finished. So you have a beaker and you have some H2, N2, and it's about to turn into NH3, and you have reached equilibrium. That means the reaction is finished, where the amount of H2, N2, and NH3 are all constant. Not equal, but constant, and the reverse rate is equal to the forward rate. The equilibrium mixture was analyzed and found that it contains 7.38 atm of H2, so at equilibrium, you have 7.38 atm of pressure of hydrogen gas, so I put it underneath hydrogen gas, 2.46 atm of nitrogen gas, and 0.166 atm of NH3. Find Kp. So if you're at equilibrium, it is easy to find Kp using the equilibrium expression. Kp is equal to products, which is ammonia, to the second power. In this case, we are not using brackets because we have pressures, so we will just use the P. The partial pressure due to NH3, and you have to square that because of this number 2 right here, divided by the partial pressure of N2, and it's a 1 there, so to the power of 1, and the partial pressure of H2, gas to the power of 3. Okay, since you're at equilibrium, all you have to do is to plug in the numbers. So pressure of NH3 is 0.166 to the power of 2 over N2 is 2.46 to the power of 1, and 7.38 to the power of 3. Okay, go ahead and pause the video and get the answer. Okay, so when you plug that in, you should have gotten 2.79 e to the negative 5. This is Kp. So you might wonder, what is that used for? This Kp here will tell us a few things. So first, since it's very small, it's 10 to the negative 5, that means that since Kp is equal to products over reactants, and if this number is small, that means the product's amount is small and the reactant is big. That means when you're trying to make ammonia, when the reaction is done, you won't make too much NH3. You're going to have, at equilibrium, you're going to have very little NH3, and you're going to have a lot of N2 and H2 left in the beaker unreacted. Therefore, this might not be a lucrative way of making ammonia because you won't make too much of it. Okay, so let's try another example. This is the Haber process where you're making ammonia. So I'm going to write that down. N2 plus 3H2 and 2NH3. Okay, here we got the Kp from the top. Oh no, this is a different temperature, therefore it's a different Kp. They're giving us Kp here. So I always write my equation and then I write the Kp to the right, just to organize my information the same way every time, so it's easier for me to do the problems. Okay, in an equilibrium mixture of 3 gases at 500 degrees C, the partial pressure of H2 is 0.928 and that of N2. Okay, so it says in an equilibrium mixture of 3 gases. So again, you're at equilibrium. At equilibrium, you have 0.928 of this H2 of hydrogen gas. You have 0.432 and NH3 is it says, what is the partial pressure of NH3? You don't know what it is, so question mark. Okay, so it looks like they gave you the K equilibrium. You just have to plug in these numbers. So I'm going to use the same equation. Okay, not going to rewrite that. Just over here. Okay, so Kp is given 1.45 E negative 5 equals pressure of NH3 is right here's the question mark, so I'm going to put an x squared because of the 2 there, divided by over here pressure of nitrogen gas, so 0.432, and pressure of hydrogen gas 0.928 to the power of 3. Okay, so if you're solving for x, go ahead and pause the video and solve for x. So I got 2.24 E negative 3 ATM. Okay, again, X is the partial pressure of ammonia at equilibrium when the reaction is all done. So that's another way of using the equilibrium constant and the equilibrium expression to find unknowns in a reaction. Okay, let's try another one. For this problem, they want us to find Kc. Okay, so it says a closed system initially, so there is the key. It is at initial conditions. Over here, we are at equilibrium, okay, which is different from initial. Initial is when you first start the reaction and the reaction has not gone ahead yet. You just put this much in the beaker of H2 and this much of I2. So we're going to set up an ice box. Here's the I. Oops. I, here's the C, and here's the E. Stands for icebox. Okay, we're going to write the reactants, H2, I2, and HI. Okay, these are the products on the right side of that line. Okay, so it says initially, so I'm going to put that in the I for initial. You have 1 E negative 3 of H2, 2 E negative 3 of I2, and they did not mention if you had any HI initially. If they don't mention that, then you have 0. You have nothing in the beaker initially. You're just mixing the two reactants together. It says analysis of the equilibrium mixture shows, so now you're at equilibrium. Okay, so here, your E, this is the equilibrium area. Mixture shows the concentration of HI is this, 1.87 E negative 3. So this is equilibrium, so I'm going to put it where it says E, and this is equilibrium right here. Okay, so then, obviously these two, H2 and I2, are going to react to go to the right to make the product. How much you're going to use depends on the coefficient. So there's a 1 there, you're going to use minus 1x. Okay, there's a 1 there also, you're going to use one of that, minus 1x. Here there's a 2, you're going to make 2 moles of that. So whatever the x is, you just have to solve for it. Let's go ahead and I'm going to erase the 1s because it confuses me a little bit. Okay. So here, if you draw a line here, that means this is how much you start with, this is how much you're going to use, this is what you'll have in the end at equilibrium of the H2. That's how much left over. The same thing here, left over of I2 in the end. Here, you're going to make some HI, and this is how much you'll make in the end. Okay? Because you have the answer here, you can use the 2x. So 2x is what you added, so 2x would be equal to this. So here in this case, 2x is equal to 1.87 E negative 3, because that's what you made. Okay? So this is what you made, and this is also what you made. So they're equal to each other. So upon solving for x, you should get, pause the video and try to get that, please. (9.35 E negative 4 is what I got. which means this is 9.35 e negative 4. Okay, so this is 9.35 e negative 4. This is also 9.35 e negative 4. So to get the amount of H2 left over, all you have to do is subtract 1 e negative 3 minus 9.35 e negative 4, which is what you used of H2, and this is how much you'll have left over of H2. 6.50 e negative 5 here. Do the same thing here. You're subtracting 2 e negative 3 minus 9.35 e negative 4, which is 1.065 e negative 3. Okay. So now that you have the equilibrium concentrations, you can just plug that into the equilibrium expression. So the expression is products over reactants, which is HI squared, because of the 2 here, divided by products over reactants, H2, times I2 to the power of 1, both of them. And these are in molarity, so I am using the brackets. Okay, so I'm just plugging in the numbers. At equilibrium, the E, how much HI do I have? I have 1.87, which was given to me, E negative 3, in the problem, which led me to calculate these two numbers. H2, I have at equilibrium 6.50 e negative 5. And 6.065 e negative 3. I'm just carrying out more sig figs than I need. I'm not going to round until the end. So I'm going to round at the final answer. I'm going to have 3 significant figures. Okay, go ahead and plug that in the calculator. I'm going to rewrite this. It's kind of messy. 6.5 e negative 5. Okay. Ooh, I forgot to square this. There you go. .5 is the equilibrium constant. Okay, so that is bigger than 1, so that means I'm going to have more products than I'm going to have reactants when the reaction is all done. Okay, so what we did here is we tabulated all initial and equilibrium concentrations using the icebox shown here. You use coefficients to calculate the change in concentration. So minus 1x plus 2x. And then using the icebox, we plugged it in, and then we plugged it into the equilibrium expression, which is this, to find your answer.